Namaskar. I am Dr. Neeraj Upadhyay, Assistant Professor in Department of Chemistry, Dr. Hari Singh Gaur Vishwavidyalaya, Sagar. I am presenting this lecture on behalf of the author of this lecture, Dr. Sumit Kumar and Dr. Rampal Pandey. In last class, we dealt with color and constitution. There we discussed about electromagnetic behavior of light and their interaction with molecule. Molecular structure play key role in origin of color. You also learnt about chromophores and auxochromes there. We discussed about theoretical development of the field and then introduced modern theory of light behind development of color. We introduced valence bond theory and molecular orbital theory as the modern theory. The conjugations and factors affecting electron transfer were play key role in valence bond theory. In molecular orbital theory, electronic transition between occupied and unoccupied orbitals are found as the root cause of the color. This kind of electronic transition has both qualitative and quantitative aspect. It starts a separate branch of spectroscopy called electronic spectroscopy. In today's lecture, we will introduce electronic spectroscopy. On studying this module, you will be able to understand what is electronic spectroscopy, importance of Frank Condon principle for explaining intensity of vibronic spectrum, how do the dissociation and pre-dissociation of molecule happen, application of electronic spectrum, fate of electronically excited state, role of electronic transition in d metal complexes. So let us begin the lecture. Light is a flow of photons which has a well-defined linear momentum as well as energy for a particular frequency nu and wavelength lambda. Each photon can be treated as an energy packet, the energy E of which depends on frequency nu of the light by the formula E equal to h nu or E equal to hc by lambda, where h is the Planck's constant. Light has a range from radio wave to gamma rays as shown in the figure of your screen and discussed in previous lecture. But for this lecture, I am revising a bit. Radio wave has longest wavelength and smallest frequency and so has minimum energy, whereas gamma rays has the smallest wavelength and maximum frequency and so has maximum energy in the electromagnetic spectrum. The visible or white light defined as combination of wavelength from 380 nanometer to 760 nanometer. The ultraviolet light is the light having wavelength shorter than the lower limit of visible light, whereas infrared light is the light having wavelength longer than the upper limit of visible light. We discussed a bit about visible light in our previous module. The ultraviolet light, including visible light, is generally responsible for origin of electronic spectroscopy of the molecule. So let us discuss about electronic spectroscopy. Electronic spectroscopy deals with excitation of an electron from an occupied molecular state to unoccupied excited state. These excitation is a part of electronic transition. A molecule lying in a stable excited state level having vibrational and rotational level as well, and therefore total energy is equal to the sum of electronic energy, vibrational energy and rotational energy, and therefore total energy is equal to E electronic plus E vibrational plus E rotational. Here interestingly, E electronic is greater than E vibrational, which further is greater than E rotational. The vibrational level introduce coarse line while rotational level introduce fine lines in the electronic structure. For the coarse line, the total energy is equal to electronic energy plus vibrational energy. Please see figure on your screen for having visual of this. A few terms are discussed here to understand electronic spectroscopy in depth. The first term is purity. You can revise lecture number 13 for understanding purity Now we are also recalling them a little bit. Molecular orbital of the homonuclear molecule can be labeled by parity. The parity in the homonuclear molecule is deciding by observing the sign of the orbital across the center of inversion. The inversion denotes a process where a straight line passes through the center of the molecule, travel the same distance before and after the center of inversion inside the molecule and get identical arrangement. As you can imagine about all homonuclear diatomic molecules like hydrogen, if molecule contains center of inversion, then the orbital across the center of inversion, if have same sign, then it has even parity and denoted by G, that stands for German word gerade. For example, if two 1s orbital in hydrogen combine to form sigma orbital, the phase of s orbital at an equal distance from left and right from center of inversion will have same phase, and therefore sigma 1s orbital is gerade. If the orbital across the center of inversion have different signs, then it has odd parity and denoted by U, that stands for German word ungerade. An example of this is sigma 1s star orbital. It is noticeable that this is applicable only for homonuclear diatomic molecule because a heteronuclear molecule does not have a center of inversion. All transitions are not allowed. There are some rules behind this. So let's discuss about the selection rule. The selection rule for allowed transition are spin selection rule and Laporte selection rule. Interestingly, these rules are originated from conservation of angular quantum number. Total angular quantum number is the sum of orbital and spin quantum numbers along internuclear axis. The spin rule dictates that the total spin cannot change during electronic transition. The total angular momentum change should be plus minus 1 during the electronic transition. In the Laporte selection rule for centrosymmetric molecule, U to G or G to U transitions are allowed, but U to U and G to G transitions are not allowed, where U stands for ungerade and G stands for gerade. This dictates that the change in parity is necessary for the allowed transitions. Now let's discuss about the Franck-Condon principle and vibronic transitions. The origin of vibrational structure in electronic transition can be depicted by Franck-Condon principle. The electronic transition occurs faster than nuclei can respond because the nuclei are so much more massive than the electrons. In other words, electronic transition occurs so fast that the internuclear separation during transition remains almost unchanged. The quantum mechanical definition is that the intensity of vibronic transition is proportional to the square of the overlap of integral of wave function of the two states, which is known as Franck-Condon factor. The equation you can see on your screen, where S nu j nu I shows the overlap integral of the wave function and psi j and psi I shows the wave function from ground electronic state for a particular excited state psi j psi I. Figure on your screen shows that transition from ground electronic state at a low temperature and the excited state to various vibrational level, that is nu equal to 0, 1, 2, 3, etc. of the excited state upon absorption of the particular energy. The excited electronic state configuration depends upon the nuclear shift from the equilibrium position. The nuclear coordinate is generally the internuclear separation in case of diatomic molecules. The excitation from ground to excited electronic state is labeled as Q01. Now let's talk about the dissociation of the molecule. The electronic transition consists of coarse line structure due to the change in vibrational quantum number. The dissociation of the molecule takes place if the internuclear separation in the excited state is larger than that of the lower level. The electronic transition leads to a dissociation of the molecule because the vertical transition from occupied state of the ground electronic state to a state greater than the dissociation level of excited state. Therefore, the continuum is observed in place of discrete lines at the end of the spectrum that represent dissociation limit of the spectrum. Figure on your screen shows the dissociation of schematic diagram for diatomic molecules. The continuum is observed as the kinetic energy is actually in the excess after the dissociation, which means energy of the absorbed photon is equal to sum of energy of dissociation limit and extra energy that goes as kinetic energy. Now let's talk about pre-dissociation of the molecule. There are coarse line and fine structures in the electronic spectrum for vibrational and rotational levels. These structures change a lot with the change in vibrational quantum number. When a molecule is excited to the vibrational level, its electron reorganizes and undergoes internal conversion. The excess energy is given to the lattice. This process is radiationless. The spin multiplicity does not change during such internal conversions. The internal conversion mostly occurs when the two molecular potential energy curves coincide. The nuclear geometry of two states is same and state into which the molecule converts may be dissociative. So, the state close to the interaction has a finite lifetime and therefore, its energy cannot be accurately defined. Thus, the absorption spectrum is blurred close to the interaction of two potential energy surfaces. Figure on your screen shows the schematic diagram of pre-dissociation of the molecule. In other words, the pre-dissociation occurs when the bound and unbound states cross each other and thus the electron in each bound state rearranges to the unbound state. Thus, this certainly shows that the blurred zone appears in the vicinity of intersection, whereas discrete lines appear before and afterwards. Now let's talk about applications of electronic spectra. The application of electronic spectra is very important in case of homonuclear molecule such as O2 and N2. For these homonuclear molecules, the rotational lines are not absorbed as these molecule does not have permanent dipole moment. Similarly, the pure vibration lines are also not observed as the component of vibration dipole moment do not change during vibration of the molecule. But the electronic spectrum provide more information in case of gas state. The fine structure is only observed when the resolution is high enough. The resolution of the fine structure is comparatively good in case of substance in the gas state than the liquid state and solid states. Now let's talk something about electronically excited state. A molecule absorbs energy and it dissipates energy by two very interesting decay processes, radiative and radiationless. Radiative decay process is the process where the molecule dissipates photon, while in case of radiationless pathway, the excess energy converted into rotational, vibrational or translational motion of the molecule. The decay process also produces heat on thermal degradation. To understand this, we have shown here Jablonski diagram for better understanding. So, please see on your screen, we are elaborating the diagram. Jablonski energy diagram including intermediate steps is shown on your screen. The diagram shows the vertically arranged electronic states as per quantized energy, whereas the energy states are horizontally arranged for the similar multiplicity. The curvy lines shows radiationless and thick lines represent radiative transitions. Let us discuss some of the important processes involved here. The first important process is fluorescence. The molecule is excited from the ground electronic state to the excited state on absorption of photon. The excited molecule collides with each other and with the surrounding molecule. The process results dissipation of energy and hence ladder down on the quantized vibration level to the lowest vibration level as the radiationless process in the excited state. At last, the surrounding molecule cannot able to acquire the energy difference for the excited molecule to come down to the ground electronic state, and therefore, the molecules survive for a longer time at the excited state. The transition is vertical from the excited state as per Frank quantum principle. This vertical transition is called fluorescence, which is denoted by red color in your figure. The lifetime of this kind of transition is 1 to 100 nanosecond. Theoretically, the origin band absorption and the fluorescence transition are expected to be coincident. The absorption occur from ground electronic state of lowest vibrational level to various vibrational level of excited electronic state, and their transitional intensities depend upon Frank quantum principle. Oppositely, fluorescence spectrum produced by downward transition from nu dash 1 to 3 to nu double dash 0. Fluorescence occur at lower frequency than the incident transition because it occurs after the decay of vibrational energy to the surrounding molecule. A very simple example is green-orange fluorescent dye, which absorbs photon in ultraviolet region. Now, let us talk about phosphorescence. The process begins from singlet ground electronic state. The first step of the process is very much similar to that of fluorescence. Further, the presence of triplet excited state close to the singlet excited state plays a decisive role. Interestingly, the singlet and triplet excited state have a common geometry at the point of intersection of the potential energy curve for the two states. At this particular point of intersection, the unpairing of electronic spin takes place and the molecule may undergo inter-system crossing. This process is shown in figure by dark blue line. Inter-system crossing is also a non-radiative transition between two states having different multiplicity. The process of singlet-triplet transition or unpairing of electronic spin depends upon the spin-orbit coupling in the molecule. The process of inter-system crossing is relatively larger in case of heavy atoms such as sulfur because of higher spin-orbit coupling. During the phosphorescence process, an excited electron in the singlet state crosses into triplet state and dissipates energy to the surrounding molecule. Therefore, the electron steps down to the lowest vibration level of the triplet state. The electron stays in the lowest level of triplet states because triplet state is more stable as compared to singlet state. According to the Hund's rule of multiplicity, you can understand this. Finally, the large quanta of energy lie with the molecule which do not generally dissipate to the surrounding molecule. At the same time, the triplet to singlet transition is forbidden and hence the molecule emits slowly. Therefore, the emission may continue for a long lifetime that may vary from 1 millisecond to 100 seconds. The proposed mechanism for the process is defined by assuming a system where the excitation energy is trapped in a slow leaking reservoir. In last lecture, we have also discussed about pi to pi star transition, which is common in case of those compounds which contain double bonds. In this transition, an electron excites from double bond to the anti-bonding pi star orbital. The n to pi star transitions are common in case of carbonyl compounds where the non-bonding electron is excited to anti-bonding pi star orbital. Light is the electromagnetic wave where its energy defines by its wavelength or frequency. It has a range from radio wave to gamma rays. The electronic spectroscopy deals with transition occur between electronic states. Orbitals across the center of inversion having same signs show even parity and denoted by grade G. Orbital across the center of inversion with different signs show odd parity and denoted by ungraded grade, that is U. Selection rules for the allowed electronic transition are spin rule and orbital rule or Laporte rule. The intensity of vibranic transition is proportional to the square of the overlap integral of the wave function of the ground electronic state and excited electronic state. The dissociation of the molecule takes place if the internuclear separation in the excited state is larger than that of the lower level. A molecule absorbs energy on excitation and it dissipates energy through radiative and non-radiative process. Fluorescence occurs when excited electron is in the singlet state, dissipates energy to the surrounding molecule. Fluorescence occurs at lower frequency as compared to the incident transition because it occurs after the decay of vibrational energy to the surrounding molecule. Phosphorescence process occurs when an excited electron in the singlet state crosses into triplet state and dissipates energy to the surrounding molecule. Due to the violation of spin selection rule, the phosphorescence is much slower than the fluorescence and hence phosphorescence has a longer lifetime than fluorescence. In next class, we will learn about free electron model and it has been written by Sumit Kumar and Rampal Pandey. So, please keep learning and please watching the videos again and again. Thank you very much for listening me. Thanks a lot.